Let's look at this problem right here. This is another C4 problem where we've got the conservation of momentum. During a snowball fight, which for our unreasonably warm February here, we have no snow, but so be it. But during a snowball fight, and it's kind of a cool thing if you imagine some sweet action movie where the snowballs stick together because you've blasted one with another one. During a snowball fight, two snowballs traveling towards each other collide head-on. The first is moving east at a speed of 16.1 meters per second, has a mass given as 0.45 kilograms. The second is moving west, opposite direction, at 13.5 meters per second. When they collide, there's an inelastic collision, meaning they stick together, and they travel west at 3.5 meters per second. We want to know what is the mass of the second snowball here. So, got a little bit of a problem ahead of us. We know that with a problem like this, we're going to be using the large conservation of momentum. But if we just kind of draw this problem out to begin with, and like I said, this is a Unit 7 C4 problem. Technically speaking, this is problem 20.2. Put that in calligraphy. What we have here are these two snowballs. So snowball 1 is moving, we'll call east this way, at a initial velocity of 16.1 meters per second, and it has a mass of 0.45 kilograms. And then we've got snowball 2. Can I make snowball 2 yellow? Ugh. Don't get hit by the yellow snowball. Tee-hee-hee. Snowball 2 is moving directly west. We don't know its mass, but we do know that its initial velocity equals 13.5 meters per second. Okay, and we know in a type of problem like this, we're going to be setting up the long equation m1 v1i plus m2 v2i, so the initial momentums of both objects, equal the final momenta of each object. Oops, that should be an M1 there. Excuse me. How dare I? Okay, so that's what we're playing with here. The one thing in a problem like this we really need to be careful of is the fact that these snowballs are moving left and right, which is a directional issue. So in a problem like this, we need to choose, okay, which would we like to call the positive direction, which would we like to call the negative direction. After these snowballs collide and we get this kind of weird, half blue, half yellow snowball, this thing is going to be continually traveling to the west at 3.5 meters per second. And because of that, because this is kind of our initial setup up here, and this is our final setup down here, since I've got two things traveling left to the west, I'm going to call left the positive direction, okay, which makes the right a negative direction when we start this problem out. So if we're kind of starting this problem out, and we could just plug a lot of stuff into this, it's just really entering numbers at this point. We know the mass of the first snowball, 0.450 kilograms, 0.45, times our negative, because we're going in a negative direction, we declared that, of 16.1 meters per second, plus some unknown mass of the second object, times its initial velocity, which was a positive 13.5 meters per second. This equals the mass of the first snowball again, 0.45 kilograms, times its final velocity, v1f, plus the unknown mass of the second times its final velocity. Now, similar to some of the other problems we've seen here, because this is an inelastic collision and the snowballs stuck together, while we know the final velocity of this stuck together snowball is 3.5 meters per second, that is actually the velocity of both the initial snowball and the second snowball. It's both of their velocities there because they have stuck together. You can imagine both snowballs are in this mega snowball now. So what we have here is on our right side of the equation, we actually have 0.45 times 3.5 plus the second unknown mass times 3.5 as well. If we bring down some of our other numbers here, such as 0.45 times negative 16.1, we get here 7.245, let's just round that up to 7.25 Newton seconds, plus, and then it doesn't matter which order you write these first, the number or the variable, but we've got m2 times 13.5 meters per second. And then we can just go ahead and solve this. We're looking to stick together these like terms, and these numbers are going to go together, so we can do that. If we take 0.45 times 3.5, this number here is actually 1.575 or 1.58, however you like to round that. And if I subtract it from each side, those will go away. But when I subtract 1.575 from this side, I'm going to get the quantity of 5.6, so round up to 8, plus, and then I'll have my M2 again, M2 13.5 equals M2 times 3.5. If I want to kind of shuffle some quantities here, is that going to give me something I don't like? Oh, whoops. Oh, geez. Yep. Okay, so I realized there that I messed something up on the way through. It's this 5.68. I recognize that when I subtracted this 13.5 M2s over, I was going to get a negative value on the right side and a positive value on the left, which would have given me a negative mass. That doesn't make any sense. What happened, and this might happen to you, so if you ever notice that, be aware. I forgot my negative up here. I say people forget this all the time, and look, I did it too. When we have negative 7.25 minus 1.58, this is going to give us on this side a negative 8.83 Newton seconds. That works out a whole lot better. Woo! Okay, now when I subtract 13.5 M2s from each side, what I'm going to get is negative 8.83 Newton seconds equaling, and 3.5 minus 13.5 gives us negative 10. So that's negative 10 M2. Now when we divide by negative 10, we find that the second mass was equal to, as our negatives cancel, we get a positive number. That's nice, of 0.883 kilograms. And that's what we were looking for. So be careful about that. You just saw me make that error, forgetting my negative even though I had it up top. We were so careful about it. You can kind of tell if you mess something up if you're going to get a negative mass out of it. I saw I was going to get that negative mass and I realized something had to be wrong. So it's just a matter of finding it. And it's normally just, did you put the negative? Did you carry the negative? What happened to it? Okay? So as you can kind of see here when we started this problem, we drew a lovely picture of it, just kind of setting some stuff up. We knew we were going to use our conservation of momentum equation. It's nice and long there. We've got a final picture. We were able to plug everything in to the equation, and from that point it was just numbering, being careful of that negative value. Okay, so nothing too crazy there. as the objects stuck together, and our problem's finished. Mike,